Welcome back, everyone, for another deep dive into the world of physics.
Ooh.
Today, we're tackling a paper with a really intriguing title, at least to me.
Okay.
It's called New Physics in LHC Higgs Boson Pair Production.
Very cool.
So it definitely sounds like we're going to be getting into some nitty-gritty physics today.
Absolutely. We're going deep into the heart of the Higgs.
Okay.
Looking for new physics beyond the Standard Model.
Let's jump right into it.
Yeah.
For those who maybe haven't tuned in before or need a quick refresher.
Sure.
What exactly is so special about this Higgs boson? I mean, we hear about it all the time, but what makes it so groundbreaking in the world of physics?
So the Higgs boson is a really big deal in physics because it helps us understand how particles acquire mass. You see, without the Higgs boson, our universe would be a very different place.
Yeah, I'm picturing like a cosmic soup of massless particles just zipping around at the speed of light.
That's a great way to put it. It'd be chaos.
Right.
No galaxies, no stars, and definitely no podcasts.
So no us.
Exactly.
Okay, so the Higgs boson helps bring order to this chaos by giving particles mass.
Precisely. It's like the cosmic traffic cop, slowing things down and allowing them to interact and form the structures we see in the universe.
I like that. So we've got our cosmic traffic cop, the Higgs boson, but this paper we're looking at today isn't just about the Higgs itself. It's about searching for pairs of Higgs bosons, right?
That's right. You see, discovering the Higgs was a monumental achievement.
Right.
But it's really just the tip of the iceberg.
Oh.
It's like finding a single piece of a much larger puzzle. We need more pieces to see the whole picture, and that's where these Higgs pairs come in.
So by studying these Higgs pairs, we're hoping to uncover even more secrets about the universe and how it all works.
Exactly. And this paper explores some pretty wild possibilities, things that could really shake up our understanding of physics as we know it.
Okay, like what kind of possibilities? Give me a sneak peek.
Well, for starters, it explores the idea that there might be a whole hidden sector of particles out there.
A hidden sector.
Yeah. It would be like a secret room in the house of physics, and the Higgs boson might just be the key to unlocking the door.
I am so ready to open that door. What else?
And as if that wasn't enough, some physicists think the Higgs boson we know and love might not even be a fundamental particle at all.
Wait, what?
Yeah, it could be made up of even smaller, weirder particles that we haven't discovered yet.
You're really pulling me in here.
Oh, and did I mention the possibility of a Higgs imposter?
Okay, now you're just messing with me. A Higgs imposter. You've got to elaborate on that one.
I promise, I'm not making this stuff up. But we'll have to save that for later in the deep dive when we explore the truly mind-bending implications of this research.
Okay, you've definitely piqued my curiosity now. So we've got hidden sectors, potential Higgs imposters, and the possibility of the Higgs being made of even smaller particles. Where do we even begin with unpacking all of this?
Well, a good place to start is with this idea of electroweak symmetry breaking, which is a fancy way of describing how particles acquired mass in the first place. It's a central concept in particle physics, and it's really the heart of what makes the Higgs boson so special.
All right, let's break it down then. What is electroweak symmetry breaking, and what does it have to do with the Higgs?
So imagine the very early universe, just fractions of a second after the Big Bang. At that time, the universe was incredibly hot and dense.
Okay.
And the forces that govern the interactions between particles, like the electromagnetic force and the weak force.
Symmetry breaking. So what does that even mean?
It means that the universe went from a state of high energy and symmetry,
Yeah.
where the electromagnetic and weak forces were indistinguishable, to a state of lower energy and broken symmetry, where these forces separated and became distinct.
Okay, so that's the breaking part of electroweak symmetry breaking.
You got it.
But where does the Higgs boson fit into all of this?
Ah, that's the key. The Higgs boson is intimately linked to this symmetry breaking. See, in the Standard Model of particle physics, the theory that describes the fundamental particles and forces of the universe,
Okay.
this symmetry breaking is thought to be caused by a quantum field that permeates all of space and time, what we call the Higgs field.
Okay, so the Higgs field is like this invisible ocean that fills the entire universe.
That's a great analogy. And just like an ocean can have waves on its surface, the Higgs fields can have excitations or ripples, and those ripples are what we know as Higgs bosons.
So the Higgs boson is like a wave in this Higgs ocean.
You've got it. And when particles, like electrons and quarks, interact with this Higgs field, they experience resistance, which we perceive as mass. It's like Trying to move through a crowded room, the more interactions you have, the heavier you feel.
That's a great way to visualize it. So the stronger a particle interacts with this Higgs field, the more mass it has.
You got it. And the Higgs boson, being an excitation of this field, plays a crucial role in mediating this interaction.
Okay, I think I'm starting to wrap my head around this. So electroweak symmetry breaking is this cosmic event where the forces of the universe separated and the Higgs field and its associated boson, the Higgs boson, emerged, giving mass to particles.
Exactly. And that, my friend, is why the Higgs boson is such a big deal.
It's like the missing link in our understanding of how the universe came to be the way it is.
Precisely.
Yeah.
It's a fundamental piece of the cosmic puzzle.
So you're telling me the Higgs boson might not be what we think it is? That's a pretty wild concept to grasp.
It is, isn't it? But the universe is full of surprises, and physics is all about pushing the boundaries of what we think we know.
Okay, so walk me through this. What are the alternative explanations for the Higgs boson?
Well, one possibility is that the Higgs boson isn't a fundamental particle at all, but rather a composite particle.
Composite, you mean like it's made up of even smaller particles?
Exactly. Think of it like this. For a long time, we thought atoms were the fundamental building blocks of matter.
Right.
But then we discovered that atoms are made up of protons, neutrons, and electrons.
Okay.
And later, we found out that protons and neutrons are themselves made up of even smaller particles called quarks.
So you're saying the Higgs could be like the proton or neutron in this analogy, something we thought was fundamental, but is actually made up of even tinier ingredients.
Precisely. It's like discovering a secret compartment within a secret compartment.
Yeah.
It's those layers of complexity that make physics so fascinating.
Okay, I'm trying to wrap my head around this. So if the Higgs is a composite particle, what are these smaller particles that make it up? Do we know?
That's the million-dollar question. The specific nature of these hypothetical particles is still a mystery, but physicists have proposed several theoretical frameworks that could accommodate such a possibility.
Like what? Give me some examples.
One of the leading contenders is a class of theories known as composite Higgs models. These models suggest that the Higgs boson could be a bound state of new, strongly interacting particles.
Strongly interacting. Is that like the strong force that holds quarks together inside protons and neutrons?
It's similar in principle, but potentially operating at a much higher energy scale. You see, the strong force, as we understand it, binds quarks together very tightly. But in composite Higgs models, the forces responsible for binding the constituents of the Higgs would need to be even stronger.
Okay, so we're talking about some seriously strong forces here. But how would we even begin to detect these new particles if they're bound together so tightly inside the Higgs?
That's where things get really challenging. Directly observing these hypothetical particles would likely require colliding particles at energies far beyond what we can currently achieve, even at the Large Hadron Collider.
So it sounds like we might need a bigger particle accelerator. But are there any other ways to probe the nature of the Higgs and see if it's hiding something?
Absolutely. While direct detection might be beyond our current capabilities, we can still look for subtle clues and indirect signatures that could point towards a composite Higgs.
Like what? What kind of clues?
One promising avenue is to study the Higgs boson's interactions with other particles very, very carefully. You see, if the Higgs is indeed a composite particle, its interactions with other particles should deviate slightly from what we would expect if it were a fundamental point-like particle.
So it's like looking for tiny imperfections in a seemingly perfect diamond.
That's a great analogy. These imperfections, these subtle deviations from the standard model predictions, could be the smoking gun that reveals the Higgs's true nature.
This is so cool. So we're searching for these tiny anomalies in the Higgs's behavior, hoping to catch a glimpse of its inner workings. But you mentioned another, even more radical possibility, the Higgs imposter. That one really caught my attention.
Ah, yes, the dilaton. Now, this is where we venture even further into the realm of speculation, but it's a tantalizing possibility nonetheless.
Okay, you've got to tell me more about this dilaton imposter. What is it, and how could we possibly mistake it for a Higgs boson?
So the dilaton arises in certain theoretical frameworks that try to explain the nature of gravity and its relationship to the other fundamental forces.
Okay.
You see, in these frameworks, gravity is often described as a geometric property of space-time itself.
Space-time. We're going full-on cosmology now. I love it.
It's all connected. So imagine space-time as a fabric and gravity as the curvature of that fabric.
Yeah.
Now, in some theories, this fabric of space-time can undergo its own kind of phase transition, kind of like water changing from a liquid to a gas.
Okay, so we've got space-time changing its state, like water boiling.
Exactly. And just like boiling water produces bubbles, this spacetime transition can produce excitations or ripples. And one type of ripple that can emerge is the dilaton.
So the dilaton is like a ripple in the fabric of space-time.
Precisely. And here's where things get really interesting. The dilaton, in certain scenarios, can mimic the behavior of the Higgs boson.
Wait, so we could have this space-time ripple masquerading as the Higgs boson. How could we tell them apart? They sound practically identical.
You're right, it's a tricky business. Distinguishing between a dilaton and a Higgs boson would require incredibly precise measurements and a deep understanding of their subtle differences.
So how do we even begin to unravel this mystery? If the dilaton is such a good imposter, how do we catch it in the act?
Well, one key difference lies in how they interact with other particles. While both the dilaton and the Higgs boson can give mass to particles, the details of those interactions can be subtly different.
Okay, so it's like they both speak the same language, but with slightly different accents. We need to listen really carefully to tell them apart.
That's a great way to put it. And just like with language, we can learn a lot about the dilaton and the Higgs by studying how they converse with other particles.
So we need to eavesdrop on their particle conversations.
Exactly. And one of the most powerful listening devices we have at our disposal is the Large Hadron Collider.
Of course. By smashing particles together at incredibly high energies, we can create these exotic particles like the Higgs boson and maybe even the dilaton and study their every move.
You got it. And by carefully analyzing the debris from these collisions, we can piece together the properties of these particles and determine whether we're dealing with the real Higgs boson or a cunning dilaton imposter.
This is incredible. I can't believe we're even considering the possibility of space-time ripples masquerading as fundamental particles.
It's the beauty of physics. We're constantly pushing the boundaries of knowledge and exploring the universe's most mind-boggling possibilities.
Okay, so we've talked about the possibility of the Higgs boson being a composite particle, maybe even a dilaton imposter. But you mentioned earlier that these hidden sectors could really shake things up when it comes to double Higgs production. I'm still trying to wrap my head around how it all connects.
Right. It's like this, the Higgs portal, this gateway to a hidden sector of particles, could supercharge the rate of double Higgs production.
Supercharged. So we're talking about seeing a lot more of these double Higgs events if these hidden sectors are real.
Exactly. If these hidden sectors are teeming with particles that interact with the Higgs, even if it's indirectly, it's like turning up the volume on those interactions, making them easier for us to detect.
Okay, I think I'm following you. So, more hidden particles, more Higgs interactions, more double Higgs events. It's all about amplifying those signals. But if these hidden particles are, well, hidden, how do we even know where to look for these amplified signals?
That's the exciting part. We don't know exactly what to expect, which makes the search all the more thrilling. We're looking for deviations from the expected, those subtle hints that something unexpected is going on in the Higgs sector.
So we need to keep an open mind and be ready for anything.
Exactly. We might see an excess of double Higgs events at certain energies, or maybe we'll find these pairs popping up alongside other unexpected particles.
So every collision at the LHC is like opening a mystery box. We never know what we're going to find inside.
That's a great way to put it. It's what makes this research so exciting. The potential for discovery is enormous.
Yeah.
And who knows, maybe those discoveries will reshape our understanding of the universe as we know it.
It's mind-boggling to think that something as seemingly abstract as studying particle collisions could unlock such profound secrets about the universe.
It really is. It's like we're trying to decipher the universe's blueprint, one particle interaction at a time.
And the Higgs boson, this seemingly simple particle, is turning out to be a key part of that blueprint.
Absolutely. It's a gateway to understanding the fundamental nature of mass, the origins of the universe, and maybe even the existence of hidden dimensions.
It sounds like we've only just begun to scratch the surface of what the Higgs boson can tell us about the universe.
We've only just opened the door to a whole new realm of physics, and who knows what wonders await us on the other side.
I can't wait to find out. But for now, I think we've given our listeners plenty to ponder. A huge thank you to you for joining me on this incredible journey through the Higgs landscape.
It was my pleasure. Always happy to talk about the mysteries of the universe.
And to our listeners, thank you for joining us on this deep dive into the fascinating world of double Higgs production and the secrets it might hold. Don't forget to check out the show notes for links to the research paper and other resources if you're eager to explore further. Until next time, keep those minds curious and keep exploring.